If I look at this one, it says to find the sum of the infinite geometric series. Infinite geometric series, the first thing I need to do is check the r value. And this time it looks like the r value is 3/2. I'm multiplying by 3/2 each time, which means when I'm talking about infinite geometric series, I need to consider if this thing is going to converge or diverge. And in order to determine that, I look at the r value. The r value has to be between -1 and +1 for this thing to converge. And since 3/2 is not in that acceptable range, I say that this thing is going to diverge. Or you can just say that the sum does not exist. All right? Either one of those would be fine. When we're talking about an infinite geometric series, we can only find the sum if the r value is in the acceptable range. Okay? Number 14, it's the same thing. And if you notice, this is of the form a sub n a sub 1. A sub 1 times r to the n minus 1. It follows my equation for a geometric sequence exactly. So I can see that my r value right here is a 3/5. All right. And if I don't see that, I can keep plugging in values until I realize what the r value is. I can also see that the a sub 1 is a 12. Once again, I can take that right from the equation. If not, plug a 1 in, you'll get a 12 out for that first term. And so now when I look at my r value is in the acceptable range. It's between -1 and +1. So I can find the sum. So the sum equals a sub 1 over 1 minus r. And I just plug my values in. That's a 12 over 1 minus r, which is the 3/5. So I've got 12 over 2/5. And remember, dividing by a fraction, that's like a 12 over 1. Dividing by a fraction is the same as multiplying by the reciprocal. That's like multiplying by 5 over 2. So that's going to give me a 30. And that's it. So when I add this infinite number of numbers together, it gives me a 30. Okay? If I look at this one, I've got a decimal that's repeating forever, the 0.42 repeating forever. So that's the same thing as 0.424242, and that keeps going forever. And just remember, if the entire thing is repeating, I have a really great shortcut that I can use here. I have two values repeating, the 4 and the 2. So I put those two values over the same number of 9s. So two values being repeated, I put it over 2 9s. If there were 3 values being repeated, I'd put it over 3 9s. Just one value would be over just 1 9. And so when I do this, I just put it over 2 9s, and now I have to reduce this fraction. Each of these is divisible by 3. So if I do the 42 divided by 3, it gives me a 14. If I do the 99 divided by 3, it gives me a 33. And that's as simplified as it can be. 14 over 33. That's it. For this one, I want to multiply this out. And I could do 2x minus 3 times itself 5 times, but that would take forever. It would be a pain. So I have a little bit of a shortcut using Pascal's triangle. Remember, Pascal's triangle looks like this. And I'm going to write this out just as far as I need to here. Remember, I just add the terms that are next to each other. That's how I'm coming up with each of these values. I'll go one more row just so we can see the pattern continue a little bit. And when we look at Pascal's triangle, essentially this pattern continues. But I can basically take a binomial, and each of these rows in Pascal's triangle gives me kind of my coefficients as I expand this thing out. This first row is when I raise to the 0 power. This second row is when I do the first power. This is the second power, third power, fourth power, and fifth power. And really for this one, I'm doing the fifth power here. So that's the row I want. I wrote out one extra row here. But when we do this, the initial setup is the real key here. I'll start off by writing these coefficients, the 1, the 5, the 10, the 10, the 5, and the 1. And I kind of ran out of space here a little bit, so I'm going to erase these. But I'm using Pascal's triangle, so I write these down. Remember, my initial setup, I talk about doing like a plus b squared. And so as I fill this in, I fill in my a's and my b's here. This would be like a to the 5th. I always start with whatever exponent I'm dealing with. This time it's the 5th power. And I count down a to the 4th, a to the 3rd, to the 2nd, to the 1st, to the 0. The b's, I do the same thing, but in reverse. So I do b to the 4th, or sorry, b to the 5th, starting with a b to the 5th. 4, 3, 2, 1, and 0. Okay, I slap some plus signs in between, and this is my initial setup. Of course, with A and B, that's simple, but I'm just going to replace each of those with what I have written here. In other words, right here, A is actually a 2x, B is actually a -3. So I'm going to plug those in their places. So instead of an A, each time I see an A, I'm going to plug in a 2x. Each place I see a B, I'm going to plug in a -3. And now the last step of this, after the initial setup, really it's just a matter of plugging this stuff in. I'm going to simplify each piece. Like here, 2x raised to the 5th power, that's a 32x to the 5th. Here, the 2x to the 4th power, that's a 16x to the 4th times a -3. And really, this is really just a job for my calculator here. That's an 8x to the 3rd times a +9. And now I just keep simplifying this. I multiply, do a little bit of multiplying. And really, this is my last step. Let me write that a little bit bigger. So I've got 32x to the 5th. Right here, I just have the 5 times the 16 times the -3. That's a minus 240 to the 4th. So now after I've done all this simplifying and I'm multiplying all these values and I'm just left with these terms, this is the answer I get. And this is the same thing I would have gotten had I multiplied all 5 of those out, but this is quite a bit of a shortcut when you think about the headache that it would be to write that 2x minus 3 out 5 times. Okay?